If you're currently studying engineering, the most important piece of advice I can give you is to be proactive in learning about the field you want to go into. You got to start somewhere. After a few different positions in the aerospace industry, I reflect on the different types of work I've done, how I got to where I currently am, and now I'm an experienced structural analysis engineer in the aerospace industry, having worked on some pretty high profile projects as a supplier for NASA. So let's talk about my journey and how you can use it as an example to build your own. Before we get into my story of contributing to real world engineering products, be sure to tap the like button and subscribe to this channel to continue getting advice about engineering careers and how to get into them. Be sure to stick around to the end so you can take the example of my engineering journey and use it to form your own. So I started off doing a few different positions in the aerospace industry. So I was working on commercial satellites, well, NASA satellites, which pretty much falls under the category of commercial satellites. So types of scientific stuff and whatnot. So I started off doing this type of stuff in part because there was a contract early on that didn't work out. This led me to switch roles a few times. Well, first one time, and then I switched back again later when I could, just to the type of work that I enjoyed more, which I'll get more into that later. But so my first year, I was doing a lot of design, CAD modeling, 2D drawings, GD&T, that's geometric dimensioning and tolerancing. So a lot of stuff that supported just the development of the different parts of a satellite and different primary and secondary structures to hold the whole thing together, hold the components together properly and such. So a lot of just this type of work. That was my first year. So it was a lot of exposure to the types of satellite structures needed and how they end up getting designed, assembled, and first in CAD, and then how the drawings needed to be presented properly to be used in the manufacturing floor. Because the way that drawings in 2D are put together, you're keeping in mind how do these get utilized on the manufacturing floor and how do we organize them to have all the information they need for those people putting everything together and clearly communicating that, not leaving out any crucial details. And also, how different types of tolerances in GD&T are used in these drawings to make sure the parts have proper fit, form, and function. So, for instance, if you have bolt holes that are in a certain pattern and you have to make sure that two parts can properly be fastened together, the two bolt patterns have to be similarly enough patterned together that the bolts can actually properly go through all the holes, because that can be a problem because you can't always get all the bolt holes like perfectly in line. They might be like a few thousandths of an inch off, or their diameters might be a few thousandths of an inch off. So how do you line all this stuff up together with the correct tolerances so that once they're inspected and see, yeah, these bolt hole patterns are in the right places, that we can ensure that the two parts on the manufacturing floor will fit together. So just a lot of things that we're thinking about in development of structures to make sure everything gets built properly. So, like I mentioned, there was a contract that the company had that kind of fell through, didn't go as planned. And so, because of that, I found a different opportunity, and it was in systems engineering. Um, so I did that for a few years, and this involved a lot of looking at requirements for satellites and the different subsystems and system level operations that the satellite is supposed to perform in space. And so, how do these requirements support the overall mission? This was kind of good exposure to that kind of stuff. Admittedly, I really didn't think this was fun. It felt like a lot of administrative work reading these requirements that a lot of times I just didn't even understand. But I think in the long run it was helpful because I still have this foundation of requirements flow and overall what the mission is supposed to do. And it helps me understand the broader view of the satellite and what its purpose is and what each subsystem's purpose is, rather than just being super narrow in one area. So in my case, I'm not just super narrow in mechanical or structural analysis, but I have a more broad view of satellite missions. So, I mean, sometimes enduring tasks that aren't fun, it's kind of hard at the time just because it's tedious. You have to read a lot of requirements and deal with a lot of just clerical work type of stuff. But in this case, at least, you can gradually start to see a broad view of the program development, and it's helpful in the long run. So it can be worth recognizing this sometimes, not to say that every boring, tedious task is always going to be something that will reward you later, but so be selective, but in this case, it worked out, I think. And the same systems engineering position also involved a lot of observing testing of the satellite and its subsystems. So that was also, I'd say, helpful for broader program knowledge, just because you're out there and talking to the different types of engineers working on the different types of systems and subsystems. So, I mean, you could in some ways call systems engineering the jack of all trades. And ultimately, I'd say that's part of why I'm glad I'm not in it anymore, or at least one of the reasons. But it was a good way to get sort of a broader understanding of how all the different subsystems and the high level view of the satellite mission works. So, like I mentioned, I went back to the mechanical side. I've been doing a lot of structural stuff again since, more on the analysis side. So I've spent the majority of my career currently in the structural analysis side, doing primary, secondary structures, finite element analysis, which is kind of what this image is showing. It's showing a model that a structure is broken up into pieces so that the stresses and strains in each piece can be determined. Nowadays, it's done by software, so that helps a lot. There was the theory of it that was developed that could kind of be done by hand calcs, but that takes forever, of course, because you're finding the stresses and strains and loads in each individual piece of the model. So after learning both the design side and mechanical engineering for satellites, dealing with higher level system requirements and testing, I have a strong understanding of broader program needs while still working mechanical stuff. And I can understand why all these parts and assemblies are there, what they're for, rather than just viewing them as large pieces of metal to analyze. So I think that is helpful and would be helpful later if I went into more management or lead type of stuff that requires more requirement flow downs and interacting disciplinarily or interdisciplinarily and with other types of teams and such. So structural analysis, it involves a huge variety of concepts and scenarios that differ depending on the situation. So you have to learn how each type of element in the FEA model behaves in structural simulation, because you might have elements that are shaped more like rectangles. We call those plate elements, or elements that are more lines. So we might call them beam or bush or bar elements. And then there's a ton of different specifications for aircraft or satellites or different types of structural standards, such as Brune. It's a big book about how to analyze different types of aerospace components. And then performing different types of joint calculations between parts. So making sure that welds hold together properly, that fasten joints hold together properly, etc. I could go on. Structural analysis just has so many different aspects and phenomena going on in it. So gradually getting exposed to the variety of different types of analysis situations, materials, joints, etc., that's allowed me to not just take a task and perform it as instructed, but it's helped me to decide how the task is to be performed. So what is the specific methodology that we're approaching this task from? What types of FEA elements should be used? What types of specs are applicable in this particular problem or for this particular structure? What are the various points of failure of the structure? We talked about joints like welds and fasteners, and or in other cases like rivets, other types of bonds. Like so, it tends to be where these different types of bonds can actually be the biggest points of failure, or the structure itself, such as an aluminum panel or a windshield on an aircraft. How do these different points of failure come into effect? And how do we handle nonlinear situations where it's possible one of the parts is going to contact the other or get past its permanent deformation or yield strength and such? So, structural engineering, it's one of those kinds of things, like I mentioned, where you just expose yourself a ton to it, gradually understand the different aspects of it, and figure out what's the best way to tackle a certain problem or a certain structure under certain environmental conditions and such. So, that's my story about how everything kind of built up over the few different positions I've had, and how I've been able to utilize that knowledge to make an impact in structural engineering or my other positions. And I hope you found this video helpful, and I hope you're able to take some of it and the wisdom from some of it to apply it into your own career. And if you did find this video helpful, I'd appreciate it if you hit the thumbs up button, the like button, and subscribe to this channel to be in the loop to continue getting advice about engineering careers and how to be successful in them. Thanks for the view. Stay tuned and have a good one. Bye.